Hi, thank you for joining this session organized by INFORE, a European project that stands for Interactive Extreme Scale Analytics and Forecasting. My name is Antonis Deligiannakis. I'm the coordinator of the INFORE project, and I'm going to give a short overview about the challenges and objectives of INFORE. So INFORE is a research and innovation action that started about 3 years ago in January of 2019. It finished about 4 months. Athena Research Center is the coordinator, and I'm physically coordinating this action. The budget is about 4.4 million euros. This is a consortium of INFORE, consists of the Athena Research Center, National Center for Scientific Research Demokritos, RapidMiner GmbH, Barcelona Supercomputing Center, Spring Techno GmbH & Co., Marine Traffic, NATO Science and Technology Organization, NATO STO CMRE, Istituto Italiano di Tecnologia, and Fundacio Center de Regulatio Genomica. Now, let me give a brief introduction about the problems that are addressed by INFORE. So data analysts are often not expert programmers, so it's very hard for data analysts to code, program, and then debug complex data analytics tasks. And when writing the code, it often takes many hours for the code to run just to figure out that something has gone wrong. Also, it's very hard for the data analysts to optimize their code. For example, if they have some operators that can be executed over multiple available big data platforms, which ones to choose for each operator? Moreover, there are many applications that are really good at simply detecting events of interest, but it's much more useful to forecast future events of interest. For example, in the life sciences applications, it's very important to forecast the emergence of resistant cells by detecting small changes in physiological or molecular markers. At the financial sector, it's very important to forecast price swings or to detect investment opportunities. At the maritime domain, it's very important to forecast and proactively respond to some dangerous events that happen at sea, such as vessel collisions, piracy, or vessel groundings. So the question is, can we forecast the outcome of a time-consuming operation before needed to complete this operation? So the main objectives of INFORE are, first of all, to develop an open source tool to graphically design data processing workflows and complex data analytic tasks. Using this tool, the data analyst will need no programming no code to write, and the optimizer will take care of any decisions that needs to be taken care of, such as which operator will be executed in which big data platform and how the jobs at these big data platforms will start executing. Also, we develop real-time interactive machine learning and data mining tools, and to enable scalability, we make heavy use of data synopsis. Also, we have tools for efficient and accurate distributed complex event forecasting. We have 3 use cases at INFORE. The life sciences use case studies the effect of drug synergies in battling cancer. And here we have a huge number of simulations that take place, but most of them are non-promising, so the patient dies. So we need to quickly detect the most promising ones and to be able to forecast which simulations may lead to some promising scenarios and kill the rest of them. So for the financial use case, we need to be able to forecast investment opportunities, to detect whenever there is systemic risk at the stock market, or to be able to forecast price swings. At the maritime domain, we need to be able to detect complex events that happen at sea by fusing data by many sources, such as satellite data, data from unmanned vessels, data from stations at the surface, or even underwater sensors obtaining sonar data. So this is a brief introduction by me. Thank you. Please make sure to follow us at the social media. And the next speaker is Fabian Tem from RapidMiner, who will speak about the architecture of the INFORE project.
Thank you, Antonis, for the introduction. So my name is Fabian Temmer. I'm a data scientist at RapidMiner, and I will give you now a short introduction into the architecture of INFORE with the goal to make streaming data processing easy for everyone. So let me just start with just recapping what Antonis just said, the main objectives of the INFORE project regarding the architecture. So the top is what we were aimed to do. We want to build a holistic, pluggable, extensible framework for extreme scale streaming analytics. And the main objectives we focused on was we want to provide a possibility to have graphical workflow design for non-programmers, as Antonio said, so that users can actually design their streaming data analytics in a graphical way. We want to have an optimized and automatic execution of these workflows on the underlying big data platforms. And we want to integrate advanced analytics functionality like data synopsis and complex event forecasting so that the user of the INFORE architecture can simply use them in their analytics. And I just want to show now the main high-level concept we developed for the architecture to achieve these goals. So we have a few different components we designed, and one of the main important components is the graphical editor component. Obviously, if we want to provide the functionality to design graphical workflows, we need to have a component which is able to do this so that the user can actually see this. And we will see this in a few moments in more details how this is achieved in the INFORE architecture, but this is one of the main components. Next, we have the manager component, which takes this graphical workflow and actually deploys on the computing clusters on the supported big data platforms, in our case, Flink and Spark platforms. As Antonio has already said, also one of the main objectives is to automatically optimize this graphical workflow. So we have an optimizer component, which is interacting with the manager component to receive the workflow designed by the user and optimize it to have an optimized deployment plan for the workflow on the computing clusters, depending on the available resources and other conditions. And finally, we wanted to introduce and integrate so-called, we call it the advanced analytics components, could be online machine learning, synopsis data engines, complex event forecasting, maritime event detection for some support of use case, some specific things. And of course, these components on the one hand has to be developed and they are integrated in the INFORE architecture that the user can just use them like any other normal, more simple operations in the graphical workflow by just dragging and dropping them into their workflow and utilizing the functionality in their specific analysis goal. We will later see some more details about the complex event forecasting functionality and also the maritime event detection, and also some details about the optimizer components directly after my talk by Nikos Georgakos. So I will focus on the top part of this concept from the graphical editor through the managed component, how it's then actually deployed on the computing cluster. And therefore, I want to show you actually a live demo of the INFORE architecture in working. So this is RapidMiner Studio. This is normally a program to actually design batch processing data science processes in a graphical way by dragging and dropping operators in this panel in the middle. And in the INFORE project, we enhanced it with the so-called streaming extension, which allows us to design also streaming processing workflows in the same manner, and which fulfills the concept of the graphical editor component in our INFORE architecture. First step, what we have to do is we want to connect to some big data platforms, so we actually have to define these connections. So what we can start, we have here this repository, and we add here new connection objects, and you see this is still like by clicking, you say we have few connections supported. In our case, we added the Flink cluster connection. We give it a name like EBDF demo, and then you can enter the connection information you need to have to be able to connect to the big data platform in this graphical user interface. And then you can store it in the repositories. You have to do this once, and then you can utilize it in any process you want to use. And you see here I have already created some connections to a Flink cluster and a Kafka cluster, which is running on a research server, which is called Freya. That's the naming. So this is already, so can you already use it. So to showcase this demo, I want to show the different steps. So the first step is we have prepared a demo data set in this Kafka cluster. And first step in this analysis is normally just to look into the data. Therefore, we implemented operators which are called read Kafka topic, for example. So I just dragged and dropped in the operator and the Kafka connection. I connected here, and I just type in here which Kafka topic I want to use. So this is now retrieving from the Kafka topic input. I can configure some settings here, all in a graphical way. And this is just reading in, and then I can process it in a batch way. So I can, in this case, first investigate it. So I'm just running it, and it's retrieving the data from the input topic and providing it me in the result view of RapidMiner Studio. And there's some more parameters here, but the most important part, these are different messages one by one. In this case, it's only batch processing, but want to do some investigation. So this is some ship position data. We have a timestamp here. We have an identifier. And also we have a longitude and latitude here. So it just investigated this. And now I'm going back to my process panel. Next step, after I have looked into this, I want to have an analysis of this and a batch and streaming processing analysis, and therefore I actually now use the graphical editor to design this process. So, so what I have to do is I insert first the Flink cluster on which I want to run this streaming processing workflow. And then I'm using the streaming nest operator where I will design my workflow in it. And I connect it here, and this is all I need to do to actually deploy it later on the Flink cluster. I give it a name. And then I can go inside the streaming nest operator by just double-clicking on it and designing the actual process inside it. Again, I will start with my Kafka cluster because it's my input data, and I want to use Kafka source operator, which is my input data, and later I want to also push my output data also in the Kafka cluster, so I'm using a Kafka sync later. For all of this, I'm connecting this Kafka cluster here to both operators, so I'm using the same Kafka cluster, but later with different input topics, with different topic names. So I start with the Kafka source, and my simple demo process, I think about maybe the situation. I have maritime position data. I want to maybe have a simple filter to the position data. So maybe I want to filter for ships which crossing a specific threshold in the latitude coordinates. So I'm just using a filter stream operator here, which I'm connecting to the Kafka source, and the key was called latitude, and I'm just copy and pasting the threshold coordinates here. So I'm configuring here, and when they are crossing this line, I want to create a warning message. So I'm adding a map stream, which I'm calling here message, and I'm also copying the actual message I want to add there. So in this case, it's just a warning, ship enters critical zone. This is just a simple example for the demo purpose. And then finally, I want to push this output data to the output EBDVF topic. And now I just click on the run button. So I've designed the streaming process, click on the run button, and it's now deploying on the Flink cluster. And while doing this, I go back to my presentation to actually show you how this is internally working. So what you see here, the concept of the manage component, and on the top level, you see the actual RapidMiner Studio with the operators. And you may have seen no of the operators are actually technology dependent. There's nothing of Flink or Spark in it. It's all the logical functionality. This is the only thing which the user has to worry about, how this is the analytic logic is built up. The manager component convert this into a framework independent graph, so RapidMiner independently, and then convert it depending on the connection I provided to a Spark or Flink specific one, so that can actually be deployed there. So going back to my process, it's now deployed here. We can monitor it. We see it's running, and I can finally, so we have it now running on the Flink cluster, and I can finally go to my third process, which is also using, again, the read Kafka topic operator now for the output, and then do some post-processing that's just dragging and dropping in so that we can investigate it a bit more, a bit easier. And now in the output topic, we have the messages now a bit more easy distributed. And you see here, the message was entered for the events which were crossing the latitude the latitude position. So let me just go back to the presentation. So again, the overview over the INFORE architecture. I hope I could show you how we can utilize the top graphical editor, the manager component, to design workflows in a graphical way and actually deploy them on computing cluster. And just want to really shortly show you how you integrate the advanced analytics components. We could go back. So in this example, we had the streaming analysis process, and we used a simple filter to do the actual analytics. This is obviously relatively simple, but we could also, for example, just use the complex event forecasting component instead of the filter. No, should not delete this one. Instead of the filter, just connect it here, connect the output. I need a complex event forecast, the Kafka cluster also for the communication, and the Flink cluster where it should be deployed. Well, I've already set this up. And then I have to have a bit more complex, more advanced parameterization of this. But now I could utilize the complex event forecasting to actually do the filtering instead of the simple filter, and can utilize this functionality in my process and could deploy this process. So this is the INFORE architecture in a nutshell. In a few minutes, as I said, we see a bit more details later about the complex event forecasting and the maritime event detection. And now Nikos Giatrakos will talk about the optimizer component. Thank you.
Thank you, Fabian. So, hello, everyone. I'm Nikos Giatrakos from Athena Research Center, and we are going to continue by talking about cross-platform optimization of data processing workflows in INFORE, workflows such as those that were designed by Fabian in the previous presentation. So, again, to give a bit of the context here, we are operating over network architecture, which are composed of a number of clusters and data production devices. In this example, we have a black, a green, and a red cluster for exhibition purposes, and each of these clusters can run one or more big data platforms such as Apache Spark, Flink, or Kafka. Our aim is to execute workflows globally on top of this architecture, making appropriate use of resources so that our analytics keep running in a real-time fashion. So we have analytics workflows that are running continuously, and we want them to provide real-time answers to the applications that have deployed these workflows. And in order to do that, the first thing we should do is to use RapidMiner Studio and include connection components to the various clusters and big data platforms that we have available. This is what you see over here on my mouse pointer. The second thing we should do is to use a streaming optimization operator, which is provided by RapidMiner Studio, which essentially instructs the INFORE architecture that the workflow we are about to design should get optimized. And in order to execute the optimization process, we provide a suite of optimization algorithms to which we are going to refer shortly. So after that, we should double-click in this operator, in this streaming optimization operator, and design our workflow. What we actually design is a logical workflow. So it incorporates the application logic, but it is deprived of any physical details on the actual execution that will take place. The role of the optimization process is to come up with a physical workflow, that's what you see on the right of the screen, where for each operator, we prescribe the big data platform, the cluster, the big data platform, and the parallelism that it should be executed with. But we have different options, of course, and we should be able to judge which physical workflow is better than the other. In order to do that, we incorporate a number of performance dimensions, such as throughput, the number of tuples being processed per time unit, network and processing latency, communication cost, and so on and so forth. We can incorporate any performance dimension that is of the essence. If we do that, in this example here for a three-dimensional space, each physical workflow corresponds to a dot. And what we want to do in our optimization process is to distinguish the red dots from the blue ones. This is because the red dots are actually physical workflows that are not dominated in every performance dimension by others. And after we have that, after we have these Pareto optimal plans, as they are called, we want to deploy the physical workflow that provides the overall lowest cost, and the cost is actually computed as a weighted combination of the various performance dimensions. Furthermore, here we may have constraints to specific dimensions such as latency constraint or communication constraints. So the generic view of the optimization process looks like this. First of all, we should have some cost models in order to judge how good a placement of an operator in a cluster and big data platform is. Because we want to be able to accommodate any given operator, we do not assume we have an analytic formula that describes the performance of each operator in various clusters and big data platforms, but instead we develop a machine learning based cost model. We execute a few a priori benchmarks in order to see the execution performance of each operator under various clusters, big data platforms, and parallelization degrees. And we use the statistics that we collect from there in order to train machine learning based cost estimation models. If we have this cost model here, then the logical workflow is given to the optimizer in the form of a JSON file, and the optimization process continues by creating a number of what-if scenarios. So we start from the bottom of the workflow that I was showing in the previous slide, and we go, which we call the upstream operators, and we go to downstream operators to the end of the workflow. So for instance, the optimizer asks, what if I place this upstream operator in the black cluster using Spark? And of course, prescribing different parallelization degrees, which are omitted for exhibition purposes, for ease in the exhibition. Or what if I place this operator in the red cluster using Flink? And having done that, for every upstream operator, we proceed downstream to the workflow. Having placed the upstream operator in the black cluster using Spark, what if I place the downstream operator in the same cluster? Or what if I choose the green cluster running Flink for the downstream operator? And so on and so forth. And at each step, we aggregate performance predictions that are provided by the cost models. We have an overall cost for every possible physical workflow, and we pick the best one in order to prescribe for execution. Now, while doing so, we provide, as I said at the beginning, we have different options of optimization algorithms. Our optimization algorithms differ in the number of what-if scenarios they provide. So they trade their own execution time for the goodness, how much near to optimal is the physical plan they prescribe. And we have exhaustive search algorithms which examine every possible what-if scenario for the entire workflow. We have heuristic algorithms which for each upstream operator keeps only the what-if scenarios that are locally Pareto optimal, so up to that point of the workflow that we have examined so far. And we also have greedy solutions which keep only the best what-if scenario, the scenario with the best overall cost up to that point of the workflow we have examined so far. So having determined a physical workflow, we actually deployed it in the various clusters and big data platforms that we have available. But even if we do so, we are not done yet. What we should do next is to monitor the execution performance of the workflow so as to first collect statistics, because we need them. Using these statistics, we update our cost models incrementally. We do not need to train in anything from scratch. We avoided the cold start at the beginning, and now we have live statistics to improve our cost models. And furthermore, we monitor the execution, because if we see that the performance of the physical workflow deviates a lot from what we predicted, we perform runtime adaptation, coming up with new physical plans. In this particular example, for instance, we may have a new physical plan which switches the position of these two operators at the top of the slide. And in order to accomplish all this, the optimizer has its own architecture. We have at the bottom, we have, of course, the various clusters and big data platforms. We collect statistics via JMX and Slurm. We ingest the statistics in an LX stack. Statistics are used by the benchmarking component, as I said, in order to avoid the cold start. They are fed at runtime in the cost estimator, and then whichever optimization algorithm we choose interrogates the cost estimator to derive performance predictions. What we have finally achieved is to develop the first optimizer for cross-platform network streaming settings which can incorporate any given operator, either it is data mining, machine learning, pattern matching, or stream transformation operators that are provided by big data platforms. We provide the suitable algorithms that may be suitable for different application needs because they trade the amount of time they take themselves to execute with the goodness of solutions they provide. Our solution, optimization solutions, is tailored for streaming settings because we can provide good plans with sub-second latency, we can update our cost models incrementally, not from scratch, and we support runtime adaptation in our optimization process. And furthermore, what we do is generic enough to accommodate new optimization criteria and constraints and to be applied to any new operator that the user or UDF, user-defined function, that may be of the essence to various applications. And with that, I would like to thank you. And Elias Alevizos will follow describing the complex.
I think Miguel will take over now for the next talk.
Okay, Miguel Ponce de Leon will go on talking about tumor simulations in Infor.
Okay, can you hear me?
Yes.
Okay, good afternoon, everybody. My name is Miguel Ponce de Leon. I'm researcher at the Barcelona Computing Center, and I will be presenting the life science use case, which is in online exploration of multi-scale simulation of cancer growth. So just as a brief introduction, cancer is a group of diseases involving abnormal cell growth with the potential to invade or spread to other parts of the body. And a big challenge in treatment development is avoiding the emergence of resistant cells. So complex multi-scale models of tumor growth can allow us to run in silico experiment. And those this kind of simulation can be used to understand the mechanism behind the emergence of cell resistant and those resign more resilient treatments. So multi-scalation-based simulations allow the integration of different modeling approaches, and they can be seen as a virtual laboratory. So the idea is that we can customize these simulations to mimic a particular patient using molecular data and then run in silico experiments like a virtual human to decide which is a better treatment in order to avoid the development of cancer or the progression. So on the right side, you can see a brief overview of what this multi-scale model look like. So we have an agent-based model in which different agents represent cells, and inside the cells we have different molecular models that describe the behavior of the cell and how the cells respond to different treatments. And these cells are growing and developing in a microenvironment, and this microenvironment is used to simulate the diffusion of different molecules, such drugs. So in this simulation, we have different algorithms for simulate the different components, and those we have also different time scales in which the different processes take place. So we have developed a prototype model of a tumor growth in which we can provide a particular drug that binds to a receptor of the cell and may trigger the death of that cell. But if the cell is exposed for a long, they will develop resistance, and then they will not die because of the treatment, and they will keep growing. So the model has several components you can see, but on the context of this presentation, what it's important is that those simulations are computational demanding, so they take a lot of time to run these simulations in a computer, and they produce complex big data output, which include the positions of the cells, the state, and the state of the microenvironment at different times during the simulations. So in our use case, we want to use this simulation to optimize drug scaling, so the way or the timing in which drugs are administered into the tumor experiment. So we have the different steps. The first is the model definition, so where we define what is our model, what are the parameters, and so on and so forth. Then we have a calibration step in which use experimental data to find and tweak parameters of our model. And finally, we use our model for model exploration, which is, for instance, find the optimal treatments using optimization techniques. So this is our workflow, which is based on EMUSE, which is a framework for extreme model exploration with Swift. And the idea is that we have a workflow which could be a genetic algorithm, a sweep, a covariance matrix adaptation, any black box or derivative-free optimization technique. And also the workflows basically ask the model exploration to generate parameters. The parameters are plugged in different simulations. Simulations are run in parallel or concurrently. After the simulation finish, we gather the results, we learn from the result, and we generate parameters. So the problem here is that the parameter space are huge, even with few parameters. The evaluation of candidate parameters is computationally expensive, and most of candidate parameters are informative, so are not useful. So the solution we have found in the context of INFORE project is performing online exploration of the simulation trajectories and early discarding an informative parameter set. So speeding up the process of parameter exploration. So this is the architecture we have extended from our previous workflow. This is the online version. So now we have an online producer, which is listening the stream of the different simulations that are running in parallel, and it communicates to a complex event recognition model, which will tell or forecast if a particular trajectory is not being informative, and then it will tell the consumer that this simulation should be stopped and a new simulation should be run, so that the action is performed. So this is more or less the same, but with more details. So we got the muse that it's evaluating several parameters. Those parameters are running the Mare Nostrum supercomputer, and each simulation is streaming the data into a Kafka server, which is connected to RapidMiner. And in RapidMiner, we have implemented this complex event recognition, which is different, listening to different topics and deciding whether the simulation should be killed or it should be let run until the end. So these are just preliminary results. This is, sorry for the typo, this is a standard model exploration. So we run around 3,000 simulations, and it takes like 10 hours world time. We don't discard any simulation here. And most of the parameters here are non-informative. So in the green curve, you can see the exponential growth of cancer cells. On the contrary, when we perform the online exploration plus the early killing, we are able, we run the same number of simulations with same parameters, but we are able to discard 90% of the simulation early before they finish. So we use a third of the total computing time. So by running this online exploration and the early killing of simulation, we are able to save around 67% of the total computing time that it would take if you use the standard model exploration approach. And it also reduces the computing resources usage. So in summary, multi-scale simulation can be used to in silico investigate treatment strategies in model of cancer. Models have complex parameter spaces, which we can run in 1,000 computational demanding simulations. But online analysis of simulation trajectory can accelerate the model exploration. And this acceleration is a critical step in the roadmap to scale up simulations in size and in complexity in the road to virtual humans. So on the right side, you can see just a roadmap for future complex and bigger simulations. So that will be it. Thank you for your time. And I will introduce Holger Arndt from Spring. He will be introducing the finance use case. So thank you very much.
Oh, yeah. Hello, my name is Holger Arndt. I will present the INFORE financial use case. I'm managing director at Spring Techno, a company in SME based in Germany, and we focus on big data and artificial intelligence for professional traders in the financial markets. So there is the INFORE financial use case, and we do big data for performance. The data in the financial industry is very rapidly growing. There are about 1.5 billion new messages added every day, and the yearly growth rate is estimated at not less than 30 to 50%. We focus on hedge funds and their needs, also banks and private traders. And in the hedge fund industry, the needs are very clear. It is the so-called alpha, which says that the hedge fund wants an overperformance over the benchmark, which mostly is the S&P 500. Then our clients want portfolio optimization. They have mostly ready-made portfolios, or some portfolios they and markets they invest in, and they want to optimize inside these markets. A big point is risk management and risk mitigation. We have systemic risk as a big factor, and also hedging against downturns. And the INFORE application in the financial use case provides hedge funds with all these tools. What we do is to explore multi-layer financial dependencies to reduce systemic risk. And there is a good quote from the movie The Big Short. Let me put it this way: I'm standing in front of a burning house and I'm offering you fire insurance on it. That's what we want to do. And even we want to start earlier, when the house is not already burning, but we warn the financial players of impending risk and systemic risk. The KPIs we have for forecasting price swings and systemic risk prediction are from once to several times per day. So because of the big data load, at the moment, it's for most of our clients only possible to do the full run through the portfolio and all market players once a day, and we want to do it several times a day. And for big data and filtering, our goal, our KPI is 50% faster filtering through the INFORE engine. We implement then the benefits of INFORE to our existing portfolio of products, which is MaranTrader, ThisRisk Pro, and VectorBull as examples. And let me show you a video that gives an impression of the INFORE pilot. So the Synopsys data engine allows us to compute effectively correlations for large amounts of stocks and find the most correlated. Here you see visualizations of nodes for stocks and edges for dependencies. And the nodes are interactive and can be dragged and dropped by the user. Numerical details can be displayed in a sortable table. And to filter the edges, a range slider is implemented. Here you have a second visualization, which we call the carousel, which also gives intuitive view on larger sets on dependencies. The interactive visualization is highlighted on mouse over. And you also can find the range slider to filter the edges. And in addition, you can select a single stock to focus on and see the edges for this stock. So this gives overall a very intuitive overview on correlations that you have there. Yeah, here you can see on mouse over the user exploring different stocks. And these are several other visualizations you can combine on more complex sheets, which allow to perform more complex stock and market risk analysis. For example, you can check the historical dependencies and even forecast future dependencies. So this is an edge we have to go into the future with the exploration of dependencies. Yeah, you can analyze investment strategies based on risk mitigation and backtest and optimize the performance by minimizing risk and check this against a simple buy and hold strategy, where you just buy a stock or a portfolio and hold it through all market phases. The blue line you can see here represents a strategy to sell stocks on higher risk, which results in a better performance. Here you have another visualization for a very important feature of the INFORE financial use case, which is forecasting market prices in stock with a self-learning forecasting algorithm. And the blue lines stand for rising prices and the red lines for falling prices. And whenever the price crosses a prediction line, the prediction was successful. So this can be used by high-frequency traders just to get an overview and to trade against these predictions. So that's all for the financial use case. Thank you. And we continue with the presentation of Konstantina Beretta with the Maritime use case.
Hello and welcome. I'm Konstantina Beretta and I'm a researcher at Marine Traffic. I will start describing the maritime use case of INFORE. And the second part will be presented by Gabriele Ferre from CMRE. So the title of my presentation is Data-Driven Maritime Event Detection Forecasting over Big Maritime Data. So this is the outline of my presentation. Basically, I will start with motivation and with describing the problem, and then I will explain how INFORE helps us address our challenges. And I will just give some more insights about how some of our core components work. Marine Traffic leads this use case. Marine Traffic is the world's leading platform for offering vessel tracking services and actionable maritime intelligence based on the Automatic Identification System, AIS. And another major contributor is NATO CMRE. CMRE is the research center of NATO that conducts state-of-the-art scientific research and development activities and delivers innovative and tested solutions for maritime security and defense applications. And Gabriele will give more details about their work later. So this is a typical day at Marine Traffic. We have to process approximately 70 gigabytes of streams of data that needs to be processed to serve about 1 million users. And we heavily rely on the automatic identification system. The AIS is a collaborative self-reporting system that allows marine vessels to broadcast their information to nearby vessels and ground-based stations. It is based on VHF communication, and although it was first developed in order to avoid collisions between vessels, it proved to be a very valuable source of information in order to increase maritime situational awareness. However, not every vessel carries an AIS transponder, and some of the vessels that do might not use it. For example, this is one of the most searched vessels on the marine traffic website. Its name is Advendaria 1. It was first sized in Gibraltar because it was thought that it would deliver oil to Syria. So right when it was released and it began its journey in the Mediterranean, it switched off its transponder when it reached off the coast of Syria. However, it was spotted by one of our customers, anchor trackers, using satellite imagery, Sentinel-1, Sentinel-2, and Planet Labs satellite images. So the problem that we need to tackle is to increase maritime situational awareness by combining global views of data, like AIS and satellite images, with local views of data, like data from thermal cameras and acoustic data. The challenges that we have in this respect is first, of course, the large amounts of data that we need to process, the streaming fashion of vessel tracking data that come in high data rates, the data fusion of heterogeneous sources of data, so data come in different formats and different specifications. And we, of course, need to curate the data, we need to clean the data. And last but not least, we need to derive actionable intelligence out of maritime data. So how we address these challenges in INFORE? The aim is to develop complex event detection and forecasting techniques, to be able to develop techniques for multi-sensor fusion, to use data synopsis in order to address the scalability problems of large streaming data, to be able to design easily interactive data science workflows. We do so by using the RapidMiner UI that Fabian showed earlier. And we do all of the above in order to produce actionable information to increase the value of the input data. So the data sets that we process are AIS data, both real-time and historical, Copernicus satellite images, acoustic data, and data from thermal cameras. So provide these data sets as input to our workflows. Where necessary, we apply object detection techniques, more specifically vessel detection techniques, and we derive vessel positions from all these different sources of data. Then these positions are fused in our fusion engine, and individual positions are assigned to vessel trajectories. These trajectories then are fed to the synopsis data engine in order to create synopsis like simplified trajectories with fewer positions per trajectory in order to be processed more easily in the next steps of the processing chain. Then once we have simplified tracks, we are able to derive simple events that can be combined and can produce complex events. Now let's dive into some individual components. How we detect vessels in satellite imagery, and we have combined AIS data automatically with satellite images, Sentinel-1 and Sentinel-2, and we have trained a model that is able to detect vessels in images, and then we are able to detect vessels when fresh images arrive. How we perform data fusion. So once we have the detected vessels, we have a distributed framework that is able to assign individual positions to known vessel tracks in order to fill in the gaps of the trajectories. Then we have the maritime event detection component. This is the one that we have, the infrastructures that we have in our premises. We have a batch layer that is able to distributively process AIS historical information, and we combine this with a real-time layer that is able to process in a distributed way multiple streams of AIS data. And we do all this in order to be able to derive events. So the simple events are the events that are building blocks of more complex events. So examples of simple events that we are able to derive are turn events, acceleration events, route deviations, when a vessel navigates into shallow waters, proximity events, when two or more vessels are too close together, and last but not least, an event that is triggered when a vessel goes off AIS coverage or intentionally switches off its transponder. This is the AIS off event. So once we have the simple events in place, we are able to combine them to produce more meaningful complex events, like, for example, the legal phasing event. So here we use the event for forecasting system of NCSR. Elias will explain that later. And we have a simple rule that takes into account navigation information about vessels, like, for example, the speed. So in case the speed is in the range of the typical speed of fishing vessels while they are fishing. And we have an event type IAS off. So when a fishing vessel has switched off its transponder, it's very likely that it is about to perform an illegal phasing event. So here you can see also our visualization component that shows the complex and the simple events that we are able to derive in real time. So I think that's it. I hope I didn't take too much time. So thank you for your attention. And I think the next one is Elias.
Gabriele.
Gabriele, yes, sorry.
Share. Second. Do share. Okay. Hi. Do you see the screen?
Yes.
Yes.
Okay. So good afternoon. My name is Gabriele Ferri, and I'm a research scientist at the NATO STO Center for Maritime Research and Experimentation in La Spezia, Italy. And I will talk about the development of a robotic hybrid network for coastal surveillance that is part of the INFORE maritime use case that Costantina was talking before. Okay. So this is a picture of the use case that we are developing and we are going to test in February here in La Spezia. The objective is to create a synergy between global and local view sensors for a MSA application. The objective is to create a way for multimodal smart sensing and data fusion to support the decision maker of the system. As you can see, the system and the use case will be divided into two different kinds of sensor. We will have a global view sensor. Mainly, we are analyzing during this work data coming from the Sentinel multispectral instrument and SAR from the Sentinel satellites, and data produced by the AIS from the vessels. The first objective of this sensor is to provide a global view of the area and to cue in some way the robotic network. And then we pass to the local view sensor, in which we will have a local robotic network. I will talk more about this in the next slide, that in a cooperative and autonomous way detect and track the target and sending information to the Infor system. There will be also a fixed thermal camera to work in cooperation with the robots. This information will be fed into the Infor MSA and decision support platform for the complex event detection. For example, if the vessel is fishing in an unauthorized area. To focus on our network, on the network of hybrid robotic network, we have to say that the idea for MSA application is to use a network of silent, long endurance, cooperative, passive sensing robots. Passive means that you hear for the acoustic noise produced by vessel. That will be composed of liquid robotics wave gliders that are surface vehicles, as you can see here, that move exploiting the power of the waves, and OEXC autonomous underwater vehicles. You can see them here. The objective is to create a way for early, stealthy vessel detections. Obviously, they will be silent. They will be not visible because they are underwater and the surface vehicle are very low on the water surface, and to offer a persistent coverage of an area. Robots will share data fusion and will cooperate with the onshore thermal optical camera. But we have to say that the robots have limited speed and also bearing only measurements, because in the passive sonar, you only measure bearings to the target. To cope with this, we propose that cooperative autonomy, in particular autonomous decision-making and data fusion, are the key driver to improve detection, classification, tracking, and localization performance. But how to do this? To do this, we have developed an occupants grid mapping framework that is the basis for cooperative behavior. We've started from data from one sensor. Here you see test at sea that we have done with the Perseus sensor. And from the sensor, we produce position and bearing measurements. And with that, we have developed a framework of occupancy grid map that produced these occupancy maps. What is an occupancy map? Occupancy map is a map in which each cell shows the probability that a target is at a certain location. As you can see here, you have a beam or yellow area. A beam because the measurements are not a location measurement, but are bearing measurements. So you have a beam of possible location of the target. So we use data fusion between the local map produced with the measurement produced on board by the vehicles and the remote map produced by the measurement received by the collaborators to produce a fused map. And we compute here, we make some computation, in particular the Laplacian, and we search for low value of this Laplacian. And you see here, this is the position of the target. Once we have this perception layer in terms of area, this is a world model that drives our decision, we can make decisions. So we propagate these maps into the future, supposing different decisions of the robot and different possible measurements, and then we select the best decision to create the most suitable geometric configuration and the most suitable configuration for what concerns the probability of detection of the sensor. This is what we have tested here. You see here the two robots, robot 1 in black and robot 2. This is the sensor footprint. In front and back of the robot, we assume a probability of detection 0 is called to the hand fire, as we say with the linear array. And here is the target, the estimated position, the square green, and the true target position. The target is doing a sort of rotated square. As you can see here, the cooperative target localization behavior is active. So the robot starts to follow the target, moving to the northwest. And when the target turns to the northeast, the target number 1 turns to east to keep the target towards broadside to enable data fusion. So we compare this with a movement, horizontal movement of the two robots, that is without autonomy, without autonomous decision, and we compare the two results. Here at the top, you can find the probability of detection in the two cases, in red with the data-driven behavior and in black with the racetrack. And as you can see, in red, we keep a probability of detection high, even if we have this area to 0. This means then the target that is faster than the sensors move inside the end fire, so a probability is 0. But the movement of the robot enables the robots to reacquire the target. While with the black one, with the racetrack, at a certain point, the target becomes 0 because the target goes outside of the footprint of the sensors. And while below, is the error and localization. We see while in red, again, is data-driven behavior, the error is limited. In black, at a certain point, you see the error becomes high because the sensor cannot see the target. So here we show how the autonomous decision, cooperative autonomous decision, can improve the target localization and the acquisition of information on the target. And here is a typical scenario, and this is will be the base of what we are going to test in February. So we have a ship that at a certain point the ship change its position, and we have a first simple event detection. For example, AIS switched off. This cue the robotic networks, the local network, with an area to be surveyed. The robot move. The camera look at the area, and we start to collecting information and to pass this information to the INFORE system for the final complex event detector. For instance, that the ship is fishing. And how to bring everything at sea. So to do that, we are using and we have worked on the ICADME cooperative autonomy framework. That is a task-oriented autonomy. This is the architecture that runs on our robot, and then we will have a multitask mission composed of the area survey task and a target localization task based on the occupancy grid that I've described. Bringing everything at sea is not simple because, above all, if you consider below the water operation, the big issue, key research area is the problem in communication, because you talk with using acoustics, so acoustic modem, and the acoustics is very complex. So the amount of bandwidth is limited. Just to make an example, more or less 60 bytes per second, so nothing respect to the above the water communication. And then the communication is also intermittent, because you may have packet loss, so it's very challenging. For this reason, we developed a communication redundancy scheme. The idea is that in each message we have encoded, trying to spare bits, encoded the contacts from different files into the past. In this way, even if we have some packet loss, we try to cope with that. We tested that during Dance 20, our last trial. So in this trial, we have our alliance, the ship, detected as the target to be detected, and also as the command and control system. And with two AUVs, that is Groucho and Harpo, they were the sensing asset, and they were towing linear arrays. So linear arrays working again in passive, as I was saying before. So working in passive, we have bearing-only measurements, but we have also another feature that is right-left ambiguity measurements. It means that when you have a linear array and you cannot establish if a measurement is coming from right and from left. So every measurement that arrives, you create two measurements. And so you have to understand which one is the correctly related to the target. For this reason, we use a multi-sensor fusion to tackle this detection and localization problem. And we had the ICADME controlling the robots and using the occupancy grid framework I was describing before. So ICADME was running on each robot and also on the ship. And the robots exchanged the bearing contacts, the position, and also with the ship. So the maps were created in real time on the ships and also on each robot. So we had three different fusion centers. And we tell these were the result. You can see here the local map. These are results computed from Groucho. So these are the real-time results from Groucho UV. Here you see the trajectory of Groucho in black and the trajectory of Harpo in red, and these are the bearing measurement. As you can see, there were some noise. Here is the local map. It is the map computed by Groucho with its own measurement, and this is the remote map. That is the map computed by Groucho with the Harpo measurement. And this is the fusion. So this is the Laplacian. So the high white is where you assume to be the target. And you can see here, this is the estimated target position, the real position, and this is the target estimated position. So very, very, very close. After a while, the ship moved. And as you can see here, the system was able to detect that. You can see here, this is the magenta circle, the estimate position. And we were able, the system was able in real time to track and detect the target. To conclude, so the concept of hybrid robotic network has been applied to the MSA use case of the INFORE project. The objective is to develop a pervasive, persistent, and scalable monitoring system to provide an effective local view. This is essential to support the decision maker activity. As I said before, autonomy and networking are recognized as the key driver to deploy this kind of system, because to manage and to handle at sea in an effective way robotic networks, we have to rely on the intelligence of the nodes. And as a next step, we will conduct the INFORE pilot site trial in February 2022 here in the La Spezia Gulf. And to conclude, the INFORE MSA use case demonstrates how the synergy of remote sensing, machine learning, big data, and autonomous robotic networks can enable the development of new generation of systems in terms of surveillance systems that are more persistent of traditional means and very effective to support decision makers. So these are the references. Thank you for your kind attention. And I will leave the stage to Elias that will talk about the complex event detector. So thank you.
Okay. Hello, can you hear me?
Yes.
Okay, let me share my screen. Yes, you can see my screen, right?
Yes.
No. Okay, so I'm going to give a brief talk about the complex event forecasting module that we are developing in the context of the INFORE project. So let me first explain a couple of things about complex event forecasting. So we're talking about forecasting of complex events. Konstantina already mentioned something about it, but first of all, we need to understand that there's not much work going on in complex event forecasting. There is considerable work in related fields like process predictions, as we see here. There are tens of papers devoted to this issue of predicting the outcome of processes, of business processes. But in the field of complex event recognition, forecasting has not received much attention. And this is the gap that we're trying to fill here in the INFORE project. So what is exactly complex event forecasting? So the general idea first is that we are dealing here with streams, real-time streams of events. You see here on the left-hand side of this figure with the green color, a stream of simple events coming into our system. These could be AIS messages or whatever other events of interest. In the maritime use case, these would be possibly AIS messages. And we also have here down here a set of complex events, definitions of complex events. You see here an example here of a pattern written SQL-like language. So we have a set of such patterns here, and the initial goal is to detect upon this stream of input events to detect instances of satisfaction of these patterns as soon as possible. So with minimal latency, and the initial outcome is another stream of complex events. Now, this is the idea of complex event recognition. Now, if we want to go beyond that, and try to perform some forecasting, what we would like to do is to also produce another stream of forecasts. And what do these forecasts tell us? They tell us whether, if and when a complex event as defined by such patterns will be detected by the by the engine here before it is actually detected. And you can imagine here very obvious patterns that we would be really interested in forecasting them. For example, collision of vessel collision. I mean, if you can forecast that some vessels are on a collision course and they will collide if no action is taken, then this would be very crucial, and we could inform authorities about such critical situations. And now moving on, the thing I'm going to present some technical details in the remainder of the talk. So first of all, let me say that there are different ways to define event forecasting. So we could also, by event forecasting, could also mean input event forecasting, that is trying to forecast the input events themselves. What are they? So for example, is a vessel going to to have a speed of a certain level or not? This could be classified as input event forecasting, but we are mostly interested in complex event forecasting. As I said, we are trying to forecast, first of all, if a complex event is going to be detected, and this you can view this as a binary classification problem, where you emit, yes or no answers. So this is a classification problem, and on top of that, we might also want to try to estimate the time that the future complex event is going to occur. And you see here, this could be viewed as a regression problem. So these are the different formulations of the event forecasting problem here. Okay, so where do you start? Let's say that you are convinced that complex event forecasting is of some value, and the question now is, where do you start? So we need, first of all, we probably need a probabilistic model, right, for this. But the problem is that in complex event recognition, there are many different formalisms and models for defining and detecting complex events. So we need to start with something simple, and this is also for presentation purposes. Let's start with something simple. Let's assume that we define patterns in terms of regular expressions and automata as we know them from introductory CS courses. And yeah, okay, so a pattern is defined as a regular expression. We assume that the stream is just composed of symbols, A's, B's, C's, and stuff like that. And so we define a pattern as a regular expression. And what we want to do is, we also assume that the stream is generated by a Markov process and with Markov dependencies. And so what we do is we consume these event streams and forecast when this regular expression is expected to be matched. That's the idea here. And we are also trying to revise these forecasts. As we receive more and more events, we're also trying to revise these forecasts. So this is the general idea. And this is a very simple example here. Let's assume that we have a stream composed of A, B, and C. These are the symbols. This is the alphabet, let's say, from which you can construct an event stream. And this is, let's say, a very simple regular expression, a pattern defined as a regular expression, where we want an A followed by C followed by C. And this is what you would get as an automaton here, right? And you could actually map this automaton into a Markov chain like this down below. And this transformation here in this example assumes that we assume that the events are identically distributed, independent and identically distributed, but there are ways to overcome this. The general idea, though, is that you have a regular expression, you can get an automaton like this, and you can convert this to a Markov model like this here, a Markov chain in this case. Now, if you do this, then you can, the idea, sorry, let me go back again. The idea in this case, what do we mean then that when is a complex event detected in this case? In this case, a complex event is detected when the automaton reaches the final state here. every time the automaton reaches a final state here, then this means that a complex event has been detected. So what do we need this Markov chain here? We need this Markov chain here in order to estimate, given that the automaton is in some other non-final state, 0, 1, or 2 here. We want to infer in how many steps or hops or events it will reach this final state. And this is exactly what we are trying to do. We are actually inferring when the complex event is detected. So this is the general idea. And so if we can train our automaton to give us a Markov chain, what can we do then? For each one of its non-final states, we can derive a distribution, a so-called waiting time distribution. You see here, for the 0th state here, the red state, you have this red distribution here. For the state number 1, the green state, you have this green distribution here. And what do these distributions tell us? They tell us the probability of reaching the final state in k hops from the current time, let's say. So for example, here, if I am in the 3rd state here, in state number 3, so this magenta distribution is activated, let's say, and this tells us that there's a probability of around 70% to reach state number 4 here in one transition from now. And there's a 0 probability to reach state 4 in 2 transitions. Why this is, you can see why this is the case, because there is no path from 3 to 4 with 2 transitions, and so on and so on. So you can do this for multiple values of the k, let's say, variable, and you can do this for all the non-final states. And this is what you get. And once you have these distributions, you can derive the various kinds of forecasts. For example, you can derive this kind of interval forecasts, as this interval is shown here, this red interval. This tells us that if I am in state number 0, I have a probability of at least 50% to reach state number 4 in 5 to 12 transitions from now. This is what this tells us. So this is the general idea of how you can take a regular expression, use it to perform complex event recognition on a stream of symbols, so a simple stream, and then convert this to a Markov chain and derive some forecasts. Now, as you can assume, there are some limitations with this formulation. So, as I said, input events are simply symbols, so they are not really events. And this is why we use classical automata. What's the alternative? We can use more powerful automata and expressions for this purpose. One of these models is the so-called symbolic regular expressions and symbolic automata. And we can also use, instead of just mapping the automaton to Markov chain, we can use more advanced statistical models like variable order Markov models, and these models have this nice feature where they allow you to remember only what is informative. So if you want to remember to have some memory before making a probabilistic inference, you have, first of all, you consume streams, and you want to make probabilistic inferences on these streams. So how do you do them? You do them by looking back into the past and what has been preceded in the stream in order to make some inference about the future. So these variable order Markov models allow you to go deeper into the past. This is an example of how you could possibly write a symbolic regular expression. You see here that this is significantly more complicated than classical regular expressions, and you see here that you can actually you can actually use various predicates. You can query the messages that you get for extra information. Like, for example, if we assume that we know we somehow the message that we get have some information about the type of the vessel. We can also write predicates like this one about whether a vessel is a fishing vessel or not. And we can combine predicates with Boolean operators and write patterns like this one. And okay, it is more complicated when you write it, but of course it provides you with more expressive power. And it usually leads to automata that are more compact. And the good thing about symbolic automata is that you can still use such techniques about, either mapping them to a Markov chain or using variable order Markov models. So they have nice mathematical properties, and so you can use them pretty much, not in exactly the same way, but pretty much in the same way as you use a classical automata and Markov models. And so, yeah, just a very simple example here of what variable order Markov models are. And we use in Infor, we use a specific type of variable order Markov models that are called prediction suffix trees. And I will explain very briefly what these are. So let's assume that you have an automaton like this. This is presented here as a classical automaton. You see here on the transition symbols, but this is done just for presentation purposes. You should assume here that on the transitions you have Boolean expressions. But for just for presentation purposes, let's assume that we have symbols here. And this here on the bottom part of the figure, you see a prediction suffix tree. We can use a training stream to learn such a prediction suffix tree, which basically tells us what we can expect with what probability given some specific context. For example, in this case, if you, let's use this left node here. This node tells us that if I have seen two A's in the stream, then the probability of seeing another A is 0.75, and the probability of seeing another B is 0.25. And this is what prediction suffix tree looks like. And the interesting thing here is that the depth of the nodes of the leaves is not the same, right? So for some it is 2, for some it is 3, depending on how informative its node is, you expand it or not. This is why they are called variable order Markov models. And okay, I'm not going to go into much detail about this. The point is that you can use this tree and this automaton then to estimate the probabilities of various paths. This tree here shows you the various paths that the automaton, this automaton here can follow and their probabilities, and you can just use this prediction suffix tree and the automaton to derive this tree of future paths and then be able to make inferences about the future behavior of the automaton and about when and if it's going to reach this final state here. And just the last slide here just shows you a couple of figures to show you how you could use this complex event forecasting functionality. Let's assume that you have this kind of area here in the sea, and you have a vessel, and you want to know whether this vessel will enter this area or not. Okay, and these arrows here are positions from the same vessel at different times, at different points in time. And you see it follows two different trajectories, this one here and this one here. And so you see here that as the vessel moves on, so this trajectory stays outside the area, this trajectory goes into the area, and you see here that the system informs us here. It has learned, first of all, it has learned that this trajectory will never cross the area and it does not produce any forecasts. And this trajectory, on the other hand, enters the area and it starts producing forecasts. And this is one way to visualize them, right? Showing an arrow here, and dark red means that there's a higher probability of entering the area. And you see here that the system has learned that this trajectory will enter the area and produces forecasts. And that's all for forecasting. Thank you very much.
Thank you, Ilya. Thank you all. So this now the time for questions and answers. If you have any questions, please post them at the chat. I haven't seen any questions yet. So maybe it's important to mention that all the components of the INFORE architecture will be made available open source. And actually the streaming extension that's led by RapidMiner is already available, and maybe Fabian can show the viewers where they can find it and use it.
Yeah, I can do it. There are no questions so far. Maybe we can start with that. So just let me share the screen. RapidMiner Studio is available for free to download in its free version. We can utilize all functionality, and then you can always go through the so-called RapidMiner Marketplace, which is also free to download, free to use, where you can use the search engine searching for the streaming extension, which is, as I called, the prototype of the INFORE architecture, and you can download it and add it to your package and can utilize the functionality I have shown here, as you see. Then you have this additional operators which you can utilize to actually deploy your streaming processes.
Okay, thank you. So I don't see any questions so far. So if you have any questions, don't hesitate to contact us, either from through the website of INFORE, or basically you can see the information that is available and presentations. We'll be happy to also to collaborate with other projects in common and targeting common goals. And I don't see anything else, any questions so far, so maybe we can finish the session right now. Thank you all for attending the session, and I hope that you have a very nice, informative EBDVF conference. Okay. Thank you. Bye.
Thank you.
Thank you. Bye.
Bye.
Goodbye. Bye.